Welcome back to Part 7 of Introduction to Inference, where we're going to be dealing with hypothesis testing. So we're going to look at an example for a hypothesis testing situation. A car manufacturer advertises that a certain model of car achieves 29 miles per gallon on average. Now, a competitor believes that that manufacturer has overstated the achievable miles per gallon. So in other words, they think that it gets less than 29 miles per gallon. Now, we test a number of cars, and for each record its miles per gallon. We calculate the sample mean being 27. Now, 27 seems less than 29, but is 27 miles per hour consistent with the manufacturer's statement that the car achieves 29 miles per gallon on average? How confident are we that the manufacturer has significantly overstated the average achievable miles per gallon? We would like to be able to make a statement such as, we're pretty sure that that average miles per gallon is less than 29, or it's believable that the average miles per gallon is equal to 29 miles per gallon. But better stated would be that we don't have enough evidence to show that the miles per gallon is anything less than 29 miles per gallon. So let's look at the different types of hypotheses. A hypothesis test for an unknown parameter is a procedure based on sample evidence and probability used to test a specific claim about the value of a parameter. So unknown population parameters that we can test are population mean, mu, sigma, population standard deviation, or p, population proportion. Compare this to confidence interval, which gives us an interval of numbers, not a believe it or don't believe it answer. Now, since a claim can either be true or false, hypothesis testing is based on two types of hypotheses. One we call the null hypothesis, and the other is the alternative hypothesis. So, null hypothesis, what is that? The null hypothesis is a statement. It's regarding the value of a parameter to be tested. We write it as H naught, H with a subscripted 0. Always a statement of equality. You're always going to see an equal sign in there. In Stat 250 will be a strict equal sign, and other statistics courses or other courses you may see it being less than or equal to or greater than or equal to or equal to. But in Stat 250 we always just used equal. This makes it easier. Is a statement of status quo or no difference, assumed to be plausible until we have evidence to the contrary. So how would we make the statement, the null hypothesis statement for the problem we just looked at? Well, the car manufacturer advertises that a certain model of car achieves 29 miles per gallon on average. A competitor believes that the manufacturer has overstated the achievable miles per gallon. So the null hypothesis would be the status quo, what is believed to be true right now. And what is believed to be true right now is what the manufacturer says, that mu equals 29. The burden now will be on us to see, or to the competitor, that it's less than 29. So the null hypothesis is what's believed to be true. So the alternative hypothesis is a claim regarding the value of a parameter to be tested. It's written as H sub A. It never contains a statement of equality. It's either less than, greater than, or not equal to. It represents the claim that we seek evidence for. There are different types of alternative hypothesis depending on the wording of the claim. So for our example of the car manufacturer, the alternative would be we believe that the mean miles per gallon is less than 29, and we need to try to prove that. So we're going to try to get from our sample evidence to prove that this is true, that the mean looks like it is less than 29 miles per gallon. So now it's time to look at the different types of alternative hypothesis. So we're going to look at the alternative hypothesis where the parameter is greater than some value. We call this a right-tailed test. Test whether the parameter is either equal to versus greater than some value. So your null hypothesis would be the parameter equals some value, and the alternative would be whatever parameter is greater than that same value that's in the null hypothesis. So let's look at an example. A car manufacturer wants to test the claim that an average miles per gallon of its new model car exceeds 31. So the null hypothesis would be that the miles per gallon equal 31, and that the miles per gallon is greater than 31 is what we're trying to get proof for, so that's our alternative. So since mu is the mean miles per gallon for our new model of car, we would properly write the null and alternative hypothesis as the null hypothesis would be mu equal 31, and the alternative hypothesis would be mu is greater than 31. Now let's look at the less than, or what we call a left-tailed test. It tests whether the parameter is equal to a value versus less than some value. So in the null hypothesis, you'd have your parameter equaling some value, but the alternative, which is what we have to try to prove, is that we think the parameter is less than some value. So let's look at an example. A bolt manufacturer wants to test the claim that the mean diameter is less than 10 millimeter. So we call that the defect rate. So the alternative, so the null would be the defect rate is 10 millimeters. The alternative is that the defect rate is less than 10 millimeters. So let mu be the proportion of defective bolts, and we'd say the null hypothesis is mu equaling 10 millimeters. The alternative would be mu is less than 10 millimeters. Now what happens if we're not exactly sure what is happening, but we know that it seems like something's happening with the mean? Quality control people like doing this type of hypothesis test. It's called the two-tailed test, and it tests whether the parameter is either equal to versus not equal to some value. So the null hypothesis would be the parameter equals some value, and the alternative is that the parameter just doesn't equal that value. We don't know if it's greater than or less than, we just know it just doesn't equal to it, or we think it just doesn't equal to it. We have to get proof for that. So let's look at an example. A bolt manufacturer suspects that the average diameter of its bolts differs from 10 millimeters. So the null hypothesis would be that mu equaled 10 millimeters, and the alternative is mu does not equal 10 millimeters. So let's take a closer look at the right-tailed test. And for this particular example where mu equals 31 is our null hypothesis, and we're testing to see if mu is greater than 31. What happens with the hypothesis test is this. Now the two distributions that you see are the null hypothesis distribution, and what we're going to find out is the null hypothesis distribution's mean is just what you see. It's got a mean of 31, and let's say sigma was given to us. The null hypothesis distribution, and the standard error I should say is 2, because remember these are all from sampling distributions. So for my sampling distribution, this is the mean and standard deviation of my sampling distribution, which we call the standard error. Now, here's two different cases. Let's say that we took a sample and we got a mean of 32 from our sample. In our hypothesis distribution, a sample of size 32 isn't unreasonable. Look at it, it's close to the middle. And the probability of getting a sample with a mean greater than that, you have a pretty large probability of that happening. So it seems like that is very plausible that 32 could live within the null hypothesis distribution. So if I took a sample and the sample mean was 32, in this case, that wouldn't be strong evidence against the null hypothesis in favor of the alternative. So we really wouldn't have enough evidence to reject the null hypothesis. Now look at the second case. Let's say that I took a sample and got a sample mean of 35. Now look at that. That's kind of far out in the right tail. This might be pretty strong evidence that the null hypothesis distribution is not correct, that it's shifted over to the right, because that is unusual that we should have gotten a mean that large. So this is what would happen is if our sample size was 35, that would probably be enough evidence to support the claim that the mean has increased from 31. And hence this is why we call it a right-tailed test, because we're looking in the right tail to see if our sample mean is far out into the right tail. If it is far out into the right tail, then that's going to be enough evidence to reject the null hypothesis in favor of the alternative. So we'll continue in part 8 with hypothesis testing.